So last week, let me briefly summarize what we did. So we studied the Kramers-Vannier duality in the context of the transverse field Ising model. And we showed in particular that if you work, so in the case of a closed chain on a fixed Hilbert space, this operation is non-invertible. It's non-invertible. Actually, it includes in particular a projector onto the even sector, which is a bit counterintuitive since we're looking for a duality. And so the resolution was that you have to extend the Hilbert space in order to allow for both types of boundary conditions, so periodic and anti-periodic boundary conditions. We wrote down 4 unitary mappings between compatible sectors, and then we were able to write down from these 4 unitaries, you can then build one unitary acting on this extended Hilbert space. One thing that was what we did as well is that we wrote down explicitly the operator that performs this duality, and as kind of obvious from the definition of the operator, this mapping does not actually depend on the choice of the original Hamiltonian. The Kramers-Vannier duality does not actually care about the actual Hamiltonian you apply down. It only cares about one thing, which is the symmetry of this model. And then it's also why we re-derived Kramers-Vannier duality from this gauging procedure to emphasize the fact that at the end of the day, it's all about the symmetry. It's all about the gauging of this symmetry. So at the end of last lecture, I briefly mentioned something about the generalization of the Ising model to a finite group, and I will briefly clarify what I meant before we move on to the next thing. So let me define some what I'm going to call the G Ising model, which is a finite group generalization of the Ising model. So the idea is to replace the initial degrees of freedom. So we had a Hilbert space that was like, this was our microscopic Hilbert space, tensor product of copies of C2 at every site. So we had spin 1/2 degrees of freedom. And I want to think of this Hilbert space actually, or rather the local Hilbert spaces, as a free vector space over Z2. Another way of saying it is that I want to think of the two states of the spin 1/2 degrees of freedom, up and down, as being labeled by the two group elements of Z2. And so the generalization I'm considering amounts to replacing this Hilbert space by this one, where now I'm promoting Z2 to any other finite, possibly in an abelian group. And so here really I mean a span. So basis vectors are really labeled by group elements. Okay. Now, how does the Hamiltonian look like? So remember, you have 2 terms in the Ising model. The first one, that was the sigma z term. It essentially forces the spin to align. So the analog of this, when you have these new degrees of freedom, will look like this. So let me write down directly what this operator is. So I have a Kronecker delta function, which is going to force 2 group elements to be the same. This is the analog of this sigma z. So it's an operator that acts diagonally by just forcing the corresponding degrees of freedom to be the same. Right? So forcing the corresponding group elements to be the same. And the second part of the Hamiltonian is the analog of the sigma x operator, which you can think of it as shifting. So flipping the spin is the same as shifting it by sort of shifting the group element. So the analog of this in the finite group case looks as follows, where I introduce this left translation operator, which acts by left multiplication. And similarly, I can define a right, an operator that acts from the right. Okay. So here we have to sum over all possible shifts. Well, for one thing, because so that the Hamiltonian will be symmetric, but also so that you get something that is Hermitian. Okay, so what is the symmetry? of this model. Well, it has a kind of ordinary symmetry, it's just a G symmetry. Instead of having a Z2 symmetry, we have a G symmetry. And the operators.
Isn't the Hermitian conjugate of the left shift the right shift?
No, it's going to be left shift with x minus 1.
Okay.
Yeah.
And so is it just the Potts model?
So in the case of, if you take an abelian group, yes. Actually, I mean, yes, I mean, I think there are several versions maybe of the Potts model, but yeah, you can think of it as a clock model. I think so. I forgot exactly how usually the Potts model is defined for more general groups, but yes, I think it's. But Potts is usually for abelian group, right? So here it can be non-abelian. So
Potts is usually for SN.
SN even? Okay, so yeah, I don't. Okay, so we have a G symmetry. So what are the symmetries of these operators? So it's by right action for all possible group elements. So why is that? Well, because I mean, since this, it forces the group elements to be the same. If you shift them by the same amount, it doesn't matter. And here, the shift that this produces will be absorbed in the sum here. It's just you change the summation variable. And now one question which I'm not going to answer right away, but like given this model and given this symmetry, what are the sectors? So by sectors, again, I mean like what are the possible boundary conditions and then the possible charge sectors. But this is not as easy to answer as in the case of Z2. I'm just going to write the kind of the algebraic structure that encodes these sectors, and we will see next week what this is exactly and what it means. Okay, what I'm interested in is the dual of this model. So the dual, so I'm just gonna give you the final result. You can sort of intuit the result by analogy with the Z2 case. And the way the dual model looks like this. So before, like the sigma z would become 1 sigma z for like the domain wall, like in between on the half integer sides. So now I have the analog of this, which is going to essentially force the corresponding domain wall degree of freedom to be the identity. And similarly for what used to be the sigma x term and become like a sigma x, now we're gonna get two shifts operators. So we get a right and a left because of some orientation conventions that you have to keep track of when it's non-abelian. But what the interesting question about this model is, what is its symmetry?
What is this EI plus 1 half?
Yeah, so this is, okay, this is really by analogy, I can write it down explicitly, but this is really forcing the corresponding domain wall degrees of freedom to be the identity. Like this, yeah. Sorry. To be the identity. So what is the symmetry? Well, although this model looks not so different from the previous model, it has a very different symmetry. And it has what we will call in a second a rep G symmetry. The reason why is because the symmetry operators, so there we had symmetry operators labeled by group elements, right? X, for instance, such that when you compose two operators, it furnishes a representation of the group. Now we have symmetry operators that are actually labeled directly by representations. And so they act as follows. So it acts diagonally, means it just multiplies the states by some number. Okay. So this number is obtained by evaluating So you have a representation rho. Let's say we take an irreducible representation. You evaluate this representation on all the group elements. You multiply the corresponding matrices, and then you take the trace. So why is that a symmetry? Well, the first operator acts diagonally as well, so then it just commutes. These are just numbers. The only thing non-trivial to check is this one. And what will happen if you act first with this operator before acting with this one? Well, for two neighboring degrees of freedom, you're going to shift one from the right by x minus 1, and the next one by x from the left. So the x and the x one will cancel, and therefore it will be symmetric. So literally just using the defining property of having a group representation.
Act non-trivially, like is this a faithful action?
Yes, it is a faithful action. Yeah, this will be this is an important point. Actually, the symmetries we will consider in a second, we will always require that they act faithfully. It's not abelian. What do you mean by abelian? Well, so actually, yes, but so let's ask what happens when you act twice with such an operator, like when you compose these two operators. So if I compose, let's say for two different representations, the result of this composition is actually going to be dictated by the tensor product of the corresponding representation, and therefore this will correspond typically to a sum of operators. So you're going to get an operator for every, so you decompose this representation into irreducible representations, and for every irreducible representation that appears in the decomposition, you get a corresponding operator. So not only it's not abelian or non-abelian, but it's not even what we usually refer to this as being non-invertible, because while you don't have, if you have such composition rule, you don't have an inverse for a given operator, because the same way you don't have an inverse of a representation, but you have a dual representation. So it's a different type of symmetry, but which emerges fairly naturally just by considering the Kramers-Vanier dual of an Ising model in the case of a non-abelian group. And so same as before, the one important question which won't address today is what are the sectors. So it's even more difficult to try to imagine what the sectors look like when you have such symmetry. But again, I will just write down the answer, and we will. So when I say sector, or when I should maybe say topological sectors more generally, I always mean combination of boundary conditions, more specifically symmetry twisted boundary conditions. So possible twists you can insert to define the twisted Hilbert spaces. And then, so you have some symmetry, which in these cases, what is a bit tricky is that the symmetry changes. The symmetry that you have left depends on the sector that you choose. And then you have to ask what are the charge sectors with respect to this symmetry. So how does the resulting Hilbert space decomposes into essentially irreps of your symmetry, right? So we will see these objects next week. But what is crucial is that this algebraic sector is equivalent to the previous one, and this will guarantee that we have indeed a duality. Okay. So the main thing I wanted to highlight was the fact that we have this non-invertible type of symmetry that emerges naturally. And in particular, what we want, and this is what we're going to do today, is that we want a framework that allows us to deal with these two types of symmetries in the same way. It's kind of put them on equal footing in such a way that we can, in particular, write down operations that map from one model to the other, even though they have very different types of symmetry structures.
Given that it's the first time I personally see this presented, this model and this refugee symmetry, can you give some, is there some nice application of this? Like what could you learn using this symmetry about this model?
Well, this is a bit of a toy model, right? I'm going to show, hopefully today or otherwise next week, some models that are not as that are related to some Heisenberg models that are more physical, that don't look as handmade, and these have already non-invertible symmetries as well. So I think it will be a bit more transparent. Yes. Okay, so the framework we want is, so we want a mathematical framework, first of all, that will allow us to deal with these two types of symmetries. And so the mathematical framework we want, we want to be able to deal with this type of operations. That when you compose two symmetry operators, you have, for instance, a fusion ring like this, and not just, it does not just furnish a representation of the group. As it turns out, requiring some fusion ring like this is not enough, because we want to be able to do sort of more with the symmetry operators. In particular, we want to be able to consider junctions of symmetry operators for various reasons, to build in particular these defect Hilbert spaces I mentioned, but also when you want to do the gauging procedure of these symmetries. And so what we need is a higher mathematical structure. We can't just require some kind of fusion ring like this. So the structure that we need, or rather the one I'm going to choose, which is not, as you will see immediately, it does not account for all possible symmetries. So this is kind of a framework that we choose, is that of spherical fusion category. And I'm going to give you like a very sort of physics-oriented definition of what it means. Okay. So a spherical fusion category, which I'm going to write C, curly C. Loosely, as I said, it's not going to be a mathematically rigorous definition, consists of a bunch of data. And I think a good thumb rule to remember is that the data I'm going to list, and I'm going to list some rules that this data has to satisfy. It's basically you want something that behaves as much as possible like representations of a group. I think it's a good thumb rule, like representations, we can tensor representations, they will decompose into irreducible representations, we can dualize representations. So essentially this is a more general setting, but all the rules I'm going to list are such that you get something that looks as much as possible like representations of a group. Okay, so what is the first piece of this definition? So we have, first of all, a collection. So usually it's referred to as objects, but I'm going to refer them because in our context, this will always correspond what I'm going to call some oriented topological lines. Which I will graphically depict as a line that is oriented, label, and with a label. And these, depending on the context, will provide us different things. So these topological lines will primarily give us the symmetry operators. And this will be what labels the symmetry operators. But it will also be what provides the twist defects, which allow us to consider symmetry-twisted boundary conditions. So that's in the Hamiltonian picture. In the Lagrangian picture, this would be lines that you can couple with your partition function whenever you have a symmetry. So the actual physics interpretation of this depends slightly depending on the context. Then we want collections, which I'm going to write like this, of local topological operators. Or defects that turn one junction line into another. So turning one line into another. So this graphically looks like this. I have a line labeled by, let's say, x1, another one labeled by x2, and I have a local operator that transforms one into the other. In practice, we will use like very specific type of operators of this form, and that I will present soon. Now this will require further that these kind of junction spaces are vector spaces, because you want to be able to sum operators in particular is a vector space. Okay. Then we want some what I'm going to call an additive structure, such that we can sum our symmetry operators in particular. So additive structure, which is really allows you to consider superposition of topological lines. And I'm going to write this down with a kind of direct sum sign. So then again, depending on the specific use of the lines, the meaning of this operation will be slightly different. So in some cases, if this line represents a symmetry operator, this will translate as just a sum of operators, like a regular sum. Whenever we use these lines to define symmetry twisted boundary condition, this will translate into a direct sum of vector spaces, the corresponding twisted Hilbert spaces. So depending on the use of the line, the actual meaning of this will be slightly different. Okay, so all the lines, all the objects can be so we can superpose lines like this. So a given line will typically be a sum of lines, and can be sometimes decomposed, but some of them cannot be decomposed. So we will call this simple. So the lines that cannot be decomposed, so that cannot be written in that form, will be called simple. So this would be like the elementary operators. This is the analog of the irreducible representations in the case of the group. Decomposed are called simple. And this satisfies some property, which is that simple lines, you cannot have a non-trivial local operator on a simple line. So satisfy. So the space of local topological operators on a simple line is just C, right? So there is a single one, if you want, the base vector in C, which is just the identity.
Can you motivate this basically?
Yeah, I'm just going to write down a slightly more general version of this. And another requirement actually is that if I take two different simple objects, x1 and x2, okay, this is 0 unless this is essentially the same operator. So this actually is to ensure faithfulness of the corresponding symmetry. So the idea is that, so let's see. So if I take, just going to put this in. Right? Let's say I have a line labeled by some object x, and it's going to act. It acts on some point charge operator. So the way it acts is like I'm going to write down the action in the way like I'm sort of pulling through this operator through the operator, kind of commutation relation, where here now it's modified. So this is going to be sort of, if I write this O, this is the action on O. And actually, when you have a non-invertible symmetry, you can get slightly non-trivial effects where you pick up some defect line in the process. So the idea is that if you were able...
The dot is also another x. What is dot dot dot?
Yes, it could be a defect line labeled by another object. But let's say we don't have one for now, it doesn't really. So if ever you had non-trivial local operators between two different lines, you would be able to essentially insert such an operator, kind of break this line, and replace it locally by another one. So that when you do this operation, if you kind of think of it visually, if I were to change this one, then that would be really the action would not be given so much by the operator x, but whatever I put here instead, right? So then you will have several operators acting in the same way, and that wouldn't be faithful. So this condition is to ensure essentially faithfulness.
Can you think of it loosely as like a diagonalization statement? Sort of like
a diagonalization? So what do you mean?
Just that like a line can only continue on being its own line and not just changing into another line and then changing back.
So this is an equivalent of, this is the analog of just a Schur's lemma, right? It's just Schur's lemma, sure. Like if you have two different E-reps, the intertwiner between the two, these are essentially intertwiners, and it has to be the identity.
But what about the first property? Simple lines satisfy that they have no operators on them, but they dense.
Well, then this wouldn't. Then they wouldn't be simple, basically. That's kind of the definition as part of this. It's part of the definition of being simple.
But actually, these operators which live on the lines, they are always have the meaning of line changing operators.
Mm-hmm.
Okay.
Yep. Okay. So let me just list two more properties about these simple objects. So we have finitely many. So this is the one strong condition. Is that we have finitely many isomorphism classes of simple objects, which I'm going to write down as a curly I with a C like this. So this is obviously this is a limiting assumption, of course, because then it means we cannot deal with this does not take into account continuous symmetries, for instance, right? And every object, so every topological line, can be is isomorphic to a direct sum of simple lines. So this is some semi-simplicity to a direct sum. This is a semi-simplicity condition, which is not necessarily physically motivated, but which makes things much nicer. So some properties are kind of physically motivated in order to have something that looks like a symmetry. Some others, so finiteness, these two in particular, are more like such that everything is nicely nice and convenient.
Can we take linear combination of lines with complex coefficients as opposed to just integer?
Not really, because you have then you have like very much like an irreducible representation of a group. You know, if you have one, it's it's like you cannot take half a vector space, right? Okay. And now the main sort of structure is what we call the monoidal structure. So this is what is going to dictate how operators compose in particular. So what is it? It's like three items. The first one is a tensor product. So here by tensor product, again, it's in some cases it's literally a tensor product of representations. In some cases it's just going to be the multiplication rule of a group. So it depends a little bit on the type of symmetry we're dealing with. Okay. We have a unit, which is this one, such that, well, as you can imagine, if you tensor with a unit, it doesn't do anything. Okay. And we have a collection of isomorphisms This collection is referred to as an associator, which essentially encode the associativity of the multiplication, which means that depending on the order, so if you have three topological lines, the order in which you fuse them to each other matters. So depending on the order, what you get is, so this again, the representation, group representation is a useful analogy. If you take tensor product of vector spaces, you don't rigorously get the same vector space. Depending on which order you take the tensor product, you would have to do, at the very least, some kind of change of basis. So this is what this type of isomorphisms captures. And they have to satisfy a coherence relation, which I will specify later in a graphical way, which is a bit more enlightening.
But what kind of what is this F like? Okay, because it's abstract, it's just some object, it's a morphism in the category. So what?
So physically, this information will capture, for instance, whether you have an 't Hooft anomaly.
No, but not physically. It's like, what is it? Is it a bunch of numbers? Is it something?
Yeah. So right now it's an isomorphism. Really, like if you think of this as vector spaces, this would just be a linear. Indeed. I will give some examples, and then I will show you explicitly what they look like for some examples. This is a junction. So as we said, the morphism, the lines, these are operators that turn a line into another. This line that you take by tensoring these three objects is not rigorously the same as this line. There is an operator, a local operator that transforms this line into another.
Operator. You say operator. You use this word a little bit loosely, right? There, for example, operator F.
Yeah,
that was just some abstract label living in this space of morphisms of category. It was not an actual operator.
Indeed. So this is a map. This is literally F here is literally a map between two objects. It's not
a map, right? X1 is not a vector space by itself.
It is a map, not a linear map. It's a map. It's a map. So we say map or morphism, indeed, usually between two objects.
So it's not a matrix.
Not in general. In general, it won't be a matrix. No.
So, but presumably this big F is.
So these are not necessarily linear maps either. No.
It's a morphism.
But I will show you specific examples where it will be clearer. Okay, and the final piece of data is so this is the spherical part, but I'm only going to give you some of it. The spherical structure. So in particular, this takes care of the fact that every object has a dual. Which corresponds to sort of changing the orientation of the corresponding line. Right? If you change the orientation, you have a corresponding dual. These duals satisfy what you would want a dual to satisfy, which is that if you take twice the dual, you go back to the original thing. And also you have maps. So you have a collection of maps of the following form, so morphism. Of this form, for instance, which is that if you take an object and you tensor it with its dual, you expect to find the unit in some decomposition when you decompose it into simple ones. Okay, it's said to be spherical. There are additional constraints, but we won't worry too much about this. Okay, so that's it for the kind of the definition.
Is it somehow related to the spherical representation theory? Spherical representation.
I don't know. So sphericality here, really this is more the pivotal structure of the category. Sphericality has to do with matching, so you can define traces then when you have this, of morphisms. And it's about the left and right trace matching. I don't know if, yeah. Okay, so what I'm going to do now is I'm going to introduce a bit of a graphical calculus to make clearer the notion of this sort of junction spaces we talk about, and also to make clearer what these symbols F are. And this is this graphical calculus that we're going to use in practice anyway. Okay, so I'm going to label this as remarks. So in practice, the junction spaces I've been mentioning, we will always, almost always, look at one specific type of junction space, which is of this form. So I'm introducing a specific notation for it because we're going to use it several times. It's a special home space. So this, we call them home space, these vector spaces of morphisms. Of the following form, where you take two objects, two simple objects. So they are all simple here. I take the tensor product and I look at whether there are operators towards another one. So this, I can rewrite it a little bit. I can decompose this tensor product. So this is an object, and all objects is the direct sum of simple ones. So I can rewrite it as the direct sum of simple ones. So by this notation, I mean all the operators that appear in the decomposition of x1 and x2. Okay, and this, the faithfulness condition we had, said that this will be one-dimensional if x4 and x3 are the same. Otherwise, it will be 0. So this object is the same as you get as many copies as C as this number, and this number is the multiplicity of 3 in the direct sum, that appear in the decomposition of x1 and x2. So generally speaking, when I take two operators, it's going to decompose as follows. So the fusion coefficients that we get, these D's, the fusion rules, are integers because they correspond to dimension of vector spaces, of these junction spaces there. So since we're going to use this a lot, I'm going to introduce a graphical notation for the local operators in these vector spaces. And so we're going to draw it like this. So graphically, this is the string diagram calculus. I'm going to represent so I have my three operators, x1 and x2, fusing into x3. If there is multiplicity, you can have several possibilities, right? So I have several types of operators. I have a vector space of such operators. So J will label some basis vector in the corresponding vector space. So I think of this as in the ket notation. I'm going to label this like that, where I'm writing down x1, x2, and x3 to know which home space I'm talking about. And here J really just labels, it's a number that labels a basis vector in the corresponding space. So this is just a basis vector of this space. So the duality structure at the level of the objects in the maps implies that we can consider also dual vector spaces. And in particular, the dual of this space I just consider is going to be isomorphic to this one. And so in the same spirit, I'm going to represent this space graph. Well, so you can just use the same sort of graphical rule. Like I'm going to draw the vectors in this one. Which in the spirit of this isomorphism, I'm going to think as kets, as bra, sorry, in, so the bras corresponding with these kets. And we choose, so we're going to choose a normalization for these basis vectors that I'm going to use throughout. So there are several choices you can make, of course. I'm going to use the simplest one. It's not necessarily the nicest one, but this is the simplest one, which amounts to the following graphical rules. So I'm choosing a normalization for these basis vectors, and it translates in particular into these graphical rules that we're going to use many times. So I'm essentially stacking the two types of junction operators that we have. So this whole thing, this whole blob, is an operator turning x4 into x3, which will only be non-zero if x4 and x3 are the same. So this must give me some delta functions which identifies x3 and x4, in which case it's just the identity, like this. And another one, so if you can think of this as some kind of orthogonality condition, and there is corresponding complete sort of completeness condition, which I'm going to put next to it. So we can have the other way around. I'm stacking the two and this is a resolution of the identity. Okay. So this is a graphical identity that we're going to use. These two, actually, we're going to use them multiple times.
I'm sorry, is it Biederharn-Eliot?
Sorry, what?
Biederharn-Eliot.
Not yet. I'm getting there. Sorry? I'm getting there. The Biederharn-Eliot is gonna be this guy, the coherence relation of this.
Not just this.
Well, this is if you want, this is like like a very specific case.
Okay, but exactly the triangle, your diagram, is it the copy? For example, the bra version. Is it just the number of a x3? Representation in the tensor product of x1 and
yes, exactly.
The number of the copy.
This labels so you have a multiplicity, and this labels from 1 to whatever the multiplicity is. Yeah.
Are you summing over k as well here, or just j?
It's supposed to be the same. Sorry, it's supposed to be j. Yeah, thank you. It's supposed to be the same. Yeah. Okay, and so I need one more graphical rule, which is going to be pertain to this isomorphisms I mentioned.
But what's going to happen if you sum unequal j and k? Because that's also allowed.
You can do it, but then it's not going to be a resolution of the identity. I don't. Yeah.
But I thought that in this graphical calculus, whatever diagram you can draw, it should.
You can draw it. No, this would make sense on its own. It's just I wouldn't have this equality there, like this. It's like completeness relation. It's really like here I'm essentially like morally, and this is just a sum over j of this, right? Just like a completeness relation like this, right? Yeah. Okay, so let's talk about now these isomorphisms F. So let me rewrite just the defining property, and we're going to write them in a way that is well, in the way we need, but hopefully that is a bit more meaningful as well. Okay, so if I consider the space of maps, of like local operators, if you want, at the junction of the tensor product of x1, x2, and x3 to a fourth operator x4, I can rewrite this operator, this Helm space. I can decompose it in various ways, and we're always gonna decompose them in terms of these kind of elementary spaces. So there are two different ways of doing it. I will first do it in symbols, then I will show you graphically. And these two decompositions amount to picking a basis. So let's say we should imagine that we are fixing a basis for these junction spaces over there, the three valent ones. So given a fixed basis, now I have two different bases for this Helm space. So the first one would be associated with this decomposition, and the second one would be associated with this one. Okay, and so the F really this isomorphism over here. This is what I'm going to write with a 4. Like given an object here, I'm picking an object that is in the decomposition of x1, x2, and x3. Given that object, I have basically a change of basis between these two choices. And I'm labeling this change of basis x1, x2, x3, and x4. Now I have an obvious block structure given by this direct sum. So what I can do is that I can sort of refine this operator and define, well, literally matrices in that case.
Sorry, is the last equality there meant to be C x3, x6 tensor with C x6?
Oh yeah, I made a typo. Yeah, x6. Actually, I had it already. Okay. Yeah, thank you. So I can. I'm writing the blocks. One block like this, and this block is really just a matrix because it's a map between vector spaces. Okay. So in the end, in that case, once at this level, we have an actual matrix, which is, so this is why I'm going through this trouble, is because at the end of the day, we're going to be dealing with Hamiltonians and all, and we want to have this in actual matrices acting on some vector space. And so graphically, how does it look like, this map? So it's a useful way of thinking about it, but this is also a graphical identity that we're going to use repeatedly, which is often referred to as an F move.
So before you had F labeled by 3 indices, now you have F labeled by 4 or 6 indices.
Indeed, because I'm kind of it's like essentially a big operator that decomposes into blocks, and I'm trying to identify a block that is as small as possible. So first, there is a block kind of decomposition by picking an object here, x4. This is this operator here, which is labeled by x1, x2, x3, and x4. And then for picking x5 and x6, I'm picking out one specific block in this isomorphism, which is this one. And so graphically, so this is the most intuitive way of thinking about it. So I have x1, x2, and x3, which I'm fusing. I'm picking one object in the result of this fusion, x4, and what I'm doing, as illustrated here, is that I'm first looking at the fusion of x1 and x2, and then I will do the fusion with x3. Right? The other way of doing it is this one. So first I'm fusing x2 and x3, and then with x1. So these two, these are just two, this is just a change of basis. And so I can write down explicitly the change of basis. These matrices provide me this change of basis. And it looks like this. X6. Okay, so I'm writing these matrices in a way that is hopefully as clear as possible. So as I said, this whole thing is a matrix, and then JK and LM, which labels basis vectors in these home spaces. These are the indices really of that matrix, the matrix indices of this matrix. So this, and just to be okay, this is a number. In that case, once you specified everything, this is just a complex number. And we refer to these numbers usually as F symbols. Okay. So now using this, so first of all, this is an identity that we're going to use a lot. And using this graphical identity, I can now spell out what is this coherence relation that I very briefly mentioned earlier, which is the consistency condition that these symbols must satisfy. So not any possible matrix doing this is allowed. It has to satisfy a coherence relation, which I'm going to write down. So I'm going to do it in a slightly heuristic way, but hopefully this will be clear enough. So this coherence relation is called pentagon axiom. And essentially, it says the following. If I'm considering a string diagram of this form, so I'm not going to label it explicitly because otherwise it's going to be a lot of labels to keep track, but this is something of the form we had over there, just with one additional object. Now I'm considering the tensor product of 4 objects instead of 3. I can do operations of this type, this sort of F move I'm going to call, which amounts to doing a change of basis, in such a way that I'm going to a configuration that looks like this. Okay. And as it turns out, you have different ways of going from this configuration to this other one. So there are 2 ways, which I'm going to draw in a similar fashion. Okay, so first I'm just looking at the left part here, and I'm doing exactly a move we have over there. And then I'm doing another one. Okay, get something that looks like this. So each operation involves like some F symbols and some sums. You can just put labels and literally plug in this formula, right? Or I can do it another way. Like this. So there is one way that takes only 2 steps, another way that takes 3 steps. And we're asking that these agree. So if I write down the change of basis from this to there following this path, it's going to give me a specific equation in terms of F symbols. If I do it the other way, it's going to give me another equation, and we ask that these are equal. So this is the consistency condition. And this consistency condition will translate into, for instance, some explicit properties, such as the fact that some symmetry operators commute with the Hamiltonian. So we're going to use them in that context. Yeah.
Is the direction of the arrows in this pentagon important? Could you just not go around the entire pentagon and come back?
Well, that's a good point. So first of all, I'm going to write down the inverse operation. So the inverse operation as an F with a bar like this, right? Okay. So you could do it the other way. I chose the direction of the arrows in such a way that the inverse does not occur, right? In that case, it's just always. Okay. So I think I will do one example now, and before we take a break. Yeah.
Question from this board.
This one?
Yeah. So in that picture, that you have a map small f from x1 to x2. This small f belongs to this home space between x1 and x2, which is a vector space.
Mm-hmm.
So I can take f and multiply it by arbitrary complex number.
Yes.
So if I start with x1, f, x2, and multiply f by a complex number, do I have to do anything to x2?
You should just, well, you mean you change the basis, for instance, by rescaling your basis vectors?
No, I'm not changing the basis, I'm actually changing the vector. So instead of f, I take 4.5.
Yeah, so this is just rescaling your basis vector, right? In that case, this is a vector space, so it's really just checking. But then, so as I said, I picked a normalization, so in principle, you don't want to, you want to use that freedom once to fix your normalization, and then you stick to this normalization. We will, so you'll see in a second, like by the way we build Hamiltonians from that, we will essentially pick basis vectors and multiply them by some coefficients, and then these coefficients will contain some dynamical information about the Hamiltonian, some purely symmetric information. I think you'll see an instance of the way we exploit this.
But if you take f and you multiply by some number, you don't need to change x1 or x2. I mean, this space, the object should stay the same. You're just changing the voltage.
Indeed. Okay, so let me do one example, or maybe two, just to illustrate a bit how these things look like in practice. Okay, so the first example we're going to do will correspond to ordinary symmetries. By that I mean invertible symmetries, possibly with some 't Hooft anomaly. So the category is what we write down like as vec G alpha. So here G is finite, it's a finite group, and alpha is some normalized representative of some cohomology class. I'm gonna explain exactly what I mean by that. So concretely, alpha, what it is, it's a map from 3 group elements to U1, which satisfy a specific defining condition, which is of this form. Okay, so this product of phases has to be 1 for all group elements G1, G2, G3, and G4, all possible combinations. Okay, so that's just the definition. Now, how does the category look like? So I'm not going to define really the whole category. I'm just going to give you what we care the most about, which are the simple objects, because at the end we can recover the other objects from the simple ones. So the simple objects, what they are so one-dimensional vector spaces that are graded by some group element. So this category, I should say, is called a category of G-graded vector spaces. And the simple objects are one-dimensional vector spaces. So as vector space is basically a copy of C, but it's graded by a group element. Now, morally, in practice, we can just sort of identify this like it will be often enough to just think of like being a group element, but the vector space structure is actually important because we want to be able to take direct sum of these guys, right? We have this additive structure. If these were literally group elements, it wouldn't make sense to sum them, to direct sum them, but they have the structure of a vector space. This is why it makes sense. That's the whole point of this category. And this...
I didn't understand. How can it be one-dimensional if it's graded by G? I mean, shouldn't it be at least as many dimensional as the size of G?
Yeah, you're right. So this one is such that, so by this object, I mean, so this is a vector space, a graded vector space, in such a way that if the component, homogeneous component given by G is, there is only one non-trivial component. This is the one corresponding to G, and in that case, it's just C. Yeah. So indeed, this is what I mean by this notation. And so as so then the monoidal structure of this is simply given by the group multiplication, which is why I'm saying it's tempted to just think of them as group elements, but you want to remember that they have this structure. So how does the associator look like, or monoidal associator, more precisely? So I'm just going to do it graphically. So first of all, there is obviously no multiplicity in that case. So I'm just going to write 1, just like it's okay. I'm picking the unique basis vector, and I'm dropping the C for convenience. I'm just labeling with the group elements. So here, because it's a group, whenever you fuse an operator labeled by G1 and G2, well, there is only one possible outcome, which is the one labeled by G1 and G2. There is no decomposition into there is no multiplicity, and there is a single output that is possible. Okay, so if I just consider this diagram, now the corresponding F symbol is simply given by the group cocycle. Right? Sorry. Okay, and in that case, so the pentagon axiom that is illustrated over there follows from this condition. And indeed, so you see we had we did 5 F moves. Here this corresponds to the 5 cocycles that I pick here. You have 3 on one side, 2 on the other side. This, if you label them G1, G2, G3, and G4, this will literally be this equation that gives you this pentagon axiom.
But you introduced this cocycle in definition of your morphism, isn't it?
Yeah, so this is part of the definition. So obviously there are several choices that are possible. Here I'm saying I'm picking a cocycle, and this will dictate what the monoidal structure is. So,
but the trivial choice, but just the identity morphism.
Indeed. So basically, what literally the isomorphism. This is just the sort of the canonical morphism in VEC, because I'm tensoring product spaces. So there is a vector, just a change of basis here, but they're all one-dimensional times this number. So
if that number is always 1, then that's the one that you're thinking about, which is the identity.
Yeah, I could choose alpha to be trivial, of course, and then it's always 1. So whenever it's not, physically it's going to correspond.
I meant that the natural morphism is the identity morphism, but we can multiply.
It's essentially, indeed, it's essentially this times, exactly. That's exactly that, yeah. Okay, I think now maybe would be a good time to take a break, and I will do some more examples afterwards. Okay, so let me, I'll do one more example. At the end of the day, these are the 2 examples I will be using mainly. And this other one is, well, the one kind of, which is the motivation for all this to some extent, which is rep G itself. Okay, so this is the category of representations of a finite group again. So the objects are finite dimensional representations of the group, finite group of G, and the maps, the morphisms, are intertwiners between these representations. So the simple objects are the irreducible representation, of course. And the basis, so in that case we have to be a bit more careful about the junction spaces. The basis vectors are from spaces of this form. So when you tensor 2 representation, and you look at the map between this and the 3rd representation. So the basis vectors are given by the Clément coefficients. So it's just a finite group version of the Clément coefficients that show up in quantum mechanics for SU2. So these are, so I'm going to write them in the specific way, these Clément coefficients, with the bar here to really make sure that, to remember that this is a map from the tensor product of V1 and V2 to V3. And here I have some placeholders, which are for whatever basis vectors I'm choosing in V1, V2, and V3. So in that case, the F symbols, or the F move, So here there could be some multiplicity. Actually, we will often make use of this multiplicity. So I have to specify some indices, and in that case, the F symbols correspond to the SIG-J symbols or the Raka coefficients, which are typically denoted by this, like this. Sorry. Okay. So these Raka coefficients can be obtained in terms of the Clebsch-Gordan coefficients. It's basically, it's 4 Clebsch-Gordan coefficients that are contracted together. So the same way as for SU2, you build the SIG-J symbols. And the fact that the pentagon equation is satisfied, then it follows so from this Biddenhahn-Elliott relation, which is kind of an early incarnation of this pentagon axiom.
Is there any LM dependence in the coefficients in this equation? No.
Is there any LM dependence?
The Raka coefficients, they probably depend on the lemma.
Yeah, sorry, you're right. I forgot to put the labels there. Yes, these are the multiplicity labels. My bad. Yeah. Okay. So we could do other examples. I will introduce other examples whenever we need them. For now, we're just gonna see what we can do with this. So what I'm gonna do now is use what we've learned, in particular the graphical calculus, in order to build the Hamiltonians, which, by definition, will have a symmetry that is given by a specific spherical fusion category. So this construction is known as anionic chains. I'm going to give the usual definition today, and then we'll see later a generalization that we need in order to talk about dualities. Okay, so first of all, the lattice, we consider a closed chain with n sides. Okay. So I'm identifying the n plus 1 and 1. For now, I'm going to assume that we work always with periodic boundary conditions. We'll see the defects next week. I'm choosing a spherical fusion category. Okay. And I pick an object. I pick an object in this category. An object that is not necessarily simple. In C. Now from this, I'm going to define a Hilbert space in the following way, which is sort of exploiting the graphical calculus So I'm going to write it down and then I will explain exactly what this means. So here the graphical calculus is the same as before. The lines are labeled by objects in my category. Simple, well, so X is not necessarily a simple object, but all the other ones have to be simple. And here's J are a multiplicity indices for the corresponding home spaces, right? I have a junction of 3 lines here, I have a corresponding home space, and J labels the...
What are these horizontal labels, for instance, M1, M2?
So this, I'm using M just to differentiate, but these are objects as well. So it's the span I'm taking is over simple objects and i's, which are the site of the, I think of them as being on the integer sides of the chain, and these j's are basis vectors in the corresponding Hom spaces.
So each basis element, if I pick given m's.
So the Hom space is not necessarily the same depending on the m that you choose. The multiplicity is not necessarily the same for different choices of m, but you always pick a basis vector in whatever Hom space you have. Let me write it down in the symbolic way, which is probably is more compact. So it looks like this. So I have a direct sum over my choices of objects, and then for every site, I have a Hom space. Something of this form. So in general, this is not going to be a tensor product space. So we're going to deal with models which are not necessarily defined on tensor product spaces, and you can think of so X, the object we choose, is the one putting some constraints between the other degrees of freedom. You can think of this choice as some kind of kinematical constraint that you can impose at the level of the Hilbert space, which prevents some configurations from occurring. Now I'm going to define what I'm going to call abstract operators. They're going to be abstract until I explain how they actually act on the Hamiltonian. In a graphical way. So for every site, I have, at a given site, I can have several types of operators, and we label some kind of flavor of which operator I have at that, one flavor of operator at the site I. And they look like this. So I won't always specify sort of the range of the sums, but from the drawing on the right-hand side, it should be clear what are they. Otherwise, I can clarify. Okay, so we have a diagram of this form. Which, even though I will specify in a second how it actually acts on the Hilbert space, here you want to think of it as a map from sort of the bottom to top. And the fact that it's stable by x at the top and the bottom, it's something that is going to preserve our Hilbert space. These things are just complex numbers. So maybe this answers a bit the question that you had. It's like here for given basis vectors k and l, right? I can choose some coefficient here which depends on these basis vectors. And these coefficients will sort of tell apart two different models with the same symmetry. This is what will contain really the dynamical information of the Hamiltonian, just these coefficients. The whole idea of this procedure is kind of to separate the definition of the Hamiltonian between a component that will be manifestly symmetric and a part that dictates whatever the physics of this model is given a symmetry.
Is it important that you sum over all y's?
Not necessarily, because actually, sorry, this depends on y. Yeah, so I could set some of this to 0. Yeah, actually, in practice, typically we will not sum over all the y's. So let me write this down in a slightly more explicit form, maybe. So this definition is useful, is nice because you kind of, it's easier to interpret it really as a map from one thing to another. But these objects not being simple, like all the graphical calculus we developed, is easier when all the objects are simple. So I'm going to expand this diagram in terms of simple objects, and it looks like this. So I'm summing over the kind of. I'm summing over these xi's, which are like simple objects that appear in the definition of x. I have also a sum over basis vectors. Now these coefficients, when I rewrite it like this, will depend on this xi. Like essentially, the idea is that here these Hom spaces are quite big if X is not simple. I'm now rewriting it in terms of simple objects, so these Hom spaces are smaller, but it's a more microscopic version of the operators, if you want. Okay, so it looks the same, but now I'm summing over all these simple objects, which I'm labeling by half integer sides, and as much as possible I'm labeling everything with integer and half integer sides to kind of keep track of the geometry. So it's the same operator, it's just I rewrote it explicitly in terms of simple objects.
Is the xi that you're summing over, the I is the same that appears in the index of?
Yeah, I mean the notation is not ideal, but these are these guys there. The 4 x's that show up over here. Okay. These are all the, I mean, yes. So it's a sum over xi minus 1/2, xi plus, okay, all these guys, yeah. Yeah, it's a bit notation heavy, so I'm trying to keep it as light as possible, but if it's not clear, yeah.
It's just 4 different simple objects.
Yeah, which are components of X. Right? And then the Hamiltonian, well, the Hamiltonian is just a sum. So again, the abstract Hamiltonian, because I haven't explained yet how these guys actually act on the operator. But the Hamiltonian then is just a sum of all the local operators I'm defining, which can, as I said, come in different flavors, labeled by n. So something like this in general. So it's a very, very general definition. Let me emphasize that I made a choice here, which will give me access to Hamiltonians with, like, let's say, well, it depends on the input, but with like a few body terms, like maybe 3 body, 4 body Hamiltonians. If I want something that is not like a larger operator, essentially, I could do exactly the same procedure, but consider something an operator like this, for instance, which would act on more sites. At the end of the day, we never needed that. Most Hamiltonians, we'll see, we're gonna get like kinds of Heisenberg-like Hamiltonians. That's enough to work with operators like this. So how does the action look like? So heuristically, so here we want to make use as much as possible of the graphical calculus that we defined. So I'm going to just do it with diagrams. I'm going to write it down once explicitly so that we have it, and then we will always be working with diagrams because otherwise it's too many symbols to keep track of. So the action of, so in the spirit of what I did last time for the pentagon axiom, you have to remember that these are labeled. I'm not labeling them for now, I'm just showing like how it's, in terms of diagrams, how it looks like. So the definition of this operator on this piece of the Hilbert space, right? So it keeps going like this. Right? So this would be the site I, right? Is defined like this. First of all, I'm stacking my object over here on top of this one. Now this stacking means that lines have to be labeled by the same thing, right? So it comes with, this is why I chose these operators to be labeled by X in such a way that this is compatible with this. I can't stack them because otherwise, because they are labeled by the same thing. And then I'm just going to use, so there is some orientation, right? Which will always be the same. I'll try to be as consistent as possible. So given that, then I can do the inverse of an F move to simplify my diagram. What we need is that we need to, this is a vector, right? Which has to be in the same vector space as the initial one, otherwise it wouldn't be an operator, it wouldn't be a Hamiltonian. So what I need is that I need to simplify this diagram so that it looks like something like this. So I do one first F move. You get something that looks like this. So I'm looking at this part over there, and I'm doing the F move, which changes the recoupling. So instead of fusing these two and then this one, I'm going to fuse these two first, which gives me this diagram. And then I'm doing it another time, another one. I'm doing it for the over here. And the results looks like this. I'm getting this bubble. You can work it out on your own and check that you get this. And this is just going to be this. I had this piece of graphical calculus as well, which just gave me the identity. So at the end of the day, this is going to be something of this form, which is indeed a vector in my initial Hilbert space. Now, of course, when you write it down explicitly, you're picking up a bunch of sums in the process and of F symbols. So I'm going to write it down once explicitly so that you have the formula, and then I will refer to it so I don't have to do it again. You need the formula, yeah. It's not, I'm going to give you directly the final result. Okay, so we have something that looks like this. So it's a bit heavy on the. Okay. So that's the action of the operator. So I've done the stacking already. Okay. And now I'm just going to give you what happens once you do the resolution, I mean, using these two F symbols. Okay. So now we have the two F symbols. So first, the inverse one. Okay, that's the first one. Now the second one. So you'll see that they share some indices. Huh? So you cannot factorize sort of the operator. Okay, and so the state part is just the kind of the initial one with some updated indices. Okay. So notice that it doesn't act on this mi minus 1 and mi plus 1. Doesn't change the labels. The F symbols depend on these indices, but it doesn't actually change them. It does change the one here, and it changes by sort of fusing the initial one with y.
Should one of the j I plus 1 halves have a tilde on top?
Over here? Yes. Good catch. Give me a second. Yes, so it should be this one. Okay.
Yeah, I'm confused about this point because the fact that you originally chose this x to be a single object, not necessarily a simple one. So it means that, okay, once you decompose x in simple objects, you get, of course, a combination of terms like that, but with just particular coefficients, relative coefficients. And once you start acting with the Hamiltonian, you may destroy these relative coefficients, and so that you won't be able to rewrite these states again in terms of a single object x. So it looks like you may get out of your Hilbert.
So you can do it. So if I take the big one here, the not simple one, then I have a much bigger Helm space. And if I look at the basis vectors in this Helm space, I can label them by essentially the simple objects appearing in X. At the end of the day, I will often use this more microscopic derivation, but yes. Okay, so that was the painful part. Now let's see about the symmetry operators. Okay, so the symmetry operators are going to be defined in a similar way.
Excuse me.
Yeah.
Is there some relation with Postnikov networks and cluster transformations?
I don't know. Sorry. Okay, so the action of a line. So here my symmetry operators are going to be labeled by simple objects as well. So this is really where this terminology in terms of lines become very explicit. So if I have a state that looks like this, so it keeps going. The action of a line, essentially, you can think of the line as acting from the bottom, as I'm kind of pasting this topological line, which is, I think of it as my symmetry operator, below the state. And now, same story as before, I want to resolve this diagram in a way such that I'm getting a superposition of states in my initial Hilbert space. So in order to do that, we're going to use the completeness relation of the the basis vectors in the Hom spaces in order to get something of this form. So something like this. So I have like so if for every piece there where I have these two lines, so I have a resolution essentially of the identity. I can use my completeness relation to get something of this form. So there is implicitly here there is a sum over this label and a sum over the corresponding basis vectors. Then I'm going to use a bunch of F moves. So as many as the number of sites n in order to, so let me put these ones there. In order to move these lines around so as to get something that looks like this. So here I'm using some F moves. Instead of, for instance, fusing these two lines and then this one, I'm saying I'm going to fuse this one and this one first. So it amounts to sort of shifting this loop away from the vertical lines. And then again, this is just the orthogonality relation of the basis vectors. So I get something of this form. Okay. So I will spare you the actual expression. Something interesting though is that the operator, so first of all, this is typically going to be a non-local operator because even though it has a kind of a local contribution to it, because these are shared indices, you naturally get actually a matrix product operator expression for these operators. But in general, this is non-local. So why does it commute? Well, this will simply follow from the pentagon equation. So it follows from the pentagon axiom. And this can be seen as follows. If I consider this complex of lines, so here, what am I doing? So there is the action of the Hamiltonian on one side, and on the other side I have the action of the line. And I've done this first step over there where I'm using my completeness relation. So it keeps going like this. Okay, I haven't used it there yet. What we want is to go from a configuration like this to a configuration like that, where I'm kind of simplifying everything. There are different ways of doing it. I could either first take care of this part and then I will take care of the symmetry. Or I can take care of the symmetry first and then do the Hamiltonian part. So this is exactly the kind of situation we had with this pentagon axiom. We had two diagrams of lines, and there are two different paths to go from the initial configuration to the final configuration. And whichever path you take, it has to be an equality. So here, these are just F moves we're going to use. So you have two different paths, and they have to be equal. And this translates into the commutation relation between the action of the symmetry operator and the action of the Hamiltonian. If you want, you can write down everything explicitly and check that it just follows from this pentagon axiom in terms of the F symbols. It's not very nice, but you can do it. Yeah.
So here, could you start with an operator that wasn't so long? So on the second line, you broke down the operator to some smaller parts. So could you start with an operator that only has finitely many of the smaller parts as opposed to all of those?
Like you would want to truncate the symmetry operator. So truncating the symmetry operator would require that you have a non-trivial map from a simple object to the identity. And that's not possible unless your object is trivial in the first place. So you cannot have truncated symmetry operators. They have to act on the whole Hilbert space. Yeah. Okay, so let's do an example now to try to fix a bit ideas. Yeah, so this, there was a paper by, I don't remember there was Zheng Wang on it, Fei Guin, and several people, specifically in the case of the Fibonacci chain. So Fibonacci is a specific type of input, describing the Fibonacci onions. And so it was like one very specific examples. Then it was generalized in this way by, there was a paper by Matthew Buchan and collaborators. Typically it was used when the input was related to some rational conformal field theory. So starting from, let's say, the Ising, the lines given by the primary operators of the Ising CFT. It was often used in that context. What we're going to see, that I'm going to provide then a generalization that we developed, which is much easier to recover, like more like condensed matter theory, condensed matter theory models, like, such as Heisenberg and everything. You can think of it as some kind of extension of temporally Lie algebra as well. If you take a specific input, then it reduces to temporally Lie algebra.
I'm not asking you to go through it in any amount of detail, but the pentagon and then the pentagon axiom relates, like, if you have 4 objects and 3 fusions.
Mm-hmm.
So can you like draw a circle around 4 lines and 3 fusions, and that is the one that you do? So
at the end of the day, it's literally going to be the same as like for the definition of here. Like for the Hamiltonian part, it would be like you will first do this one there, and then you will do the one that comes from here. And if I do the symmetry operator first, well, then I would first need to introduce the resolution there, and then it always decomposes. Yeah. More generally, it's like the idea is that if you kind of take a ball and if you look at the outside, like you can always recombine inside. It just amounts to picking a different basis for the corresponding home space. I mean, there is a more formal way of stating what I said. Okay, so let's look at an example. So without doing this, well, okay, let's do an example. So the example is going to be so really the simplest thing we can do, in the sense that we start from Z2 essentially, this vex Z2, but I will make a choice of alpha. So I'm writing down Z2, the group elements are 0 and 1, like we did last week, where the multiplication is addition modulo 2. And the alpha is defined by this equation. So here I'm really using the fact that I'm I'm labeling the group elements of Z2 as 0 and 1. So here I literally mean the product. Basically what I mean by this is that this is 1 if all the group elements are 1 and 0 otherwise. No, sorry, it's -1 and 1 otherwise. Okay. So how does the Hilbert space look like? So here I'm going to choose the object, the object X to be simply the direct sum of the simple objects, of all possible simple objects.
You mean the multiplication here is literal multiplication, not the group multiplication?
Yeah, I'm using kind of some ring structure essentially, so where I can both add the elements in Z2, but I can also multiply them. So here I really mean multiplication Okay, so the Hilbert space. So I'm just applying the definition, just going to try to rewrite it in a slightly more enlightening way. So first I'm picking, so I'm going to write it in the microscopic way, where the vertical lines, I'm going to label them by simple objects in whatever appears in the decomposition of X. Okay, so something like this, with periodic boundary conditions. And here, what is important to notice is that if I'm fixing these objects, by definition of this category, the only way to get a non-trivial home space over here is if this object, when I multiply it with this one, gives me this one. So what it means that this one has to be equal to so minus G1 plus G2, right? Mod 2. Similarly, this one has to be minus G2 plus G3. Of course, it's Z2, so the -1, I could just drop the -1, but I'm just going to keep it for visual purposes. And so at the end of the day, what it means that this Hilbert space, in that case, simplifies quite a bit. It's actually not it is actually a tensor product space, because specifying this object then fully specify these ones, and therefore these are not actual degrees of freedom. So at the end of the day, this vector space, like effectively is just this vector space, right? It's kind of the vector space of the transverse field Ising model. So these kind of tricks where we kind of translate these diagrams into something that is a bit more, bit easier to grasp, this is something that we do quite often. Often we try to see, once we wrote down the model in this way, we try to see if we can simplify a little bit and to have a nicer way of thinking about it. And then the Hamiltonian. So the Hamiltonian is going to be a sum of two types of operator. One like this. Okay, so we have two flavors of operators. And I will give you the definition. So this is for this example. It's a bit of an overkill to use this construction for this example, although because of the presence of the alpha, it is not so easy in practice to write down a lattice model that is going to have a given anomaly. This is an easy way of doing that. If you give me a group anomaly and you want to write down a model that is going to have this anomalous symmetry, that's one way of doing it. So I'm going to write the Hamiltonians in a very explicit way. So I'm going to do the second one first, the one with the 1. It's going to be a sum of 4 operators. Like this. They all come with, like, they have no non-trivial coefficient in front of them. They're all 1. It's basically all possible combinations, given that the horizontal line is labeled by 1. just this guy. And the second one going to be something similar, but this one is going to have some signs. So this one, the horizontal line is labeled by the identity, so it's going to act trivially, but there will be some signs. Okay. So just this one, you get a minus sign whenever the first index is 1. Basically, that's the rule I'm following. Okay, so now you can work on. So this is the definition. Then we can just apply. So we still have this magnificent formula over there. So you could just plug everything in to write down explicitly the operators. What we like to do is, so once we use this formula, is try to write down the final Hamiltonian in terms of explicit spin operators, because to get a feel of the physics of the model, it's often useful to rewrite it explicitly. So I'm just going to give you the answer, just so that you get a feel of how these things look like. So here the terms of the one at the top, they're kind of grouped. I group them like this. So these have the peculiarity that when you act on the Hilbert space, if these lines are 0 and this one is 0, it means that the corresponding sort of horizontal strains are going to be such that the one at the side I minus 1 is going to have to be equal to the one at the side I plus 1. It's a bit like if you think of this as the domain walls, it's basically there are no domain walls there, so the spin degree of freedom over there has to be equal to the degree of freedom over there. Similarly for this guy. And these are the opposite, are such that you have one domain wall, and therefore this one has to be the opposite of the one over there. So already this gives us, even before looking at the cocycles, this already gives us some information. So what it means is that this, so the corresponding operator, so one part of it is going to be something like this. So this takes care of where they describe the fact that the spin degrees of freedom at side I minus 1 and I plus 1 have to be equal. And then the cocycle, so there was a 1/2, right? And then the cocycle will just add a contribution from a spin Z operator at the side I minus 1. So this is really, let me just emphasize, this is kind of the alpha contribution, right? This is how the cocycle contributes. The other part, so this takes care of this state. So this operator will project out all configurations such that the spin at I minus 1 and spy I plus 1 are not the same, right? So it doesn't take care of all possible states. We have to write the other part. And the other part, so there is a minus sign that is due to the cocycle. And you get something like this. So the part in the middle, again, it has nothing to do with the cocycle. It's just to make sure that it translates the fact that there is a domain wall between the corresponding spin degrees of freedom. The two external sigma z's, they are there because of the alpha. And the other term, but the other term actually does not care for the alpha. You see, the cocycle is rarely minus 1 actually. It's only when you have specific, when all of them are 1 that you get a minus 1. So here the fact that you have a 0 horizontally, it will prevent any occurrence of a non-trivial alpha. And what you get is simply sigma z term like in the transverse Ising model. Why is that? You get a minus 1 whenever you have a domain wall here between I minus 1 and I, which is via essentially Cramer's linear duality, which is not, it's not a coincidence if it works like this. You get a term like this.
So I'm surprised because it seems to me that this second term breaks spatial parity because of this second minus sign.
Spatial parity, you mean?
You flip the chain, like you do the transformation I to minus I. Then, okay, so it seems to act differently on 0, 1 and on 1, 0 because of this relative minus sign.
Yes, so since we sum over all possible operators, at the end of the day, so basically here is just saying we don't care about whatever is on the right hand side, right? It's all about the guy over here. I could have rewritten this as a local. Actually, this.
Maybe just drop the second term.
Yeah, essentially. I could have rewritten this down.
It cancels when you sum over.
I could have rewritten this down like this. Where if this is side I minus 1 and this is I could have rewritten it down like this. I just rewrote it like this so that the two look the same, but you can write it like this as well. Yeah. Okay, and so already maybe you already guessed it, but if you switch off the alpha, you recover the transverse field Ising model. So if alpha is 1, you choose a trivial cocycle, then we recover the transverse field Ising model. So if you want this, it's like an anomalous version of the transverse field Ising model. Okay, let me just give you now the final part, which is the symmetry.
And what's the physical meaning of this anomalous version?
So, you mean apart from the fact that it has an anomaly? You're not asking about the physical.
Why don't we encounter it more often?
So this actually it's written in a bit of a funny way, but this actually occurs. It occurs at the boundary of some higher dimensional models that have like symmetry protected topological order. This on the boundary, if you write down some effective model for the boundary theory, you will get this kind of anomalous models. So this actually, this model has been studied for a while, and this is a way of recovering it in this framework. Yes. And there, the fact that because what people often do is that they they have another way of deriving this model, and then they work out what is the anomaly. Here, the anomaly, we know what the anomaly is because this was part of the definition. So sometimes, this is often the way we use this approach, is that if you think that a model has a given symmetry or a given anomaly, and maybe it's not so easy to check, if we have a way of recasting it in this language, which in some cases is not that difficult, then you know it has to have a symmetry, even if it's hard to check explicitly, it must have it by definition.
You didn't explain why your definition of anomaly coincides with the usual one.
Indeed, we will get to that next week. Yeah. So let me just write down the symmetry. So the symmetry, as an anomalous symmetry, it's not going to be on site. It's going to be given by a non-local operator, which acts as follows. So I'm going to write it down once explicit. So this is actually easier to work out than the action of the Hamiltonian. You get something that looks like this, because every local, so locally it contributes kind of all in the same way via this cocycle over here. And at the same time, it acts by translation via the Pauli X operator. Now, using the definition, there is a way of writing it down more explicitly, which is usually the way people write it down. So I think it's part of this Hamiltonian was first written down by Levin and Gu, and then I think the whole Hamiltonian was more by Xiaogangwen in some paper. So you have this Pauli X contribution, and then there is the phase, which we can write down explicitly in terms of spin operators. It's a bit of a funny looking expression, but you can check that it matches. Yeah, there are several i's. Sorry, it's a bit of a clash of So this is the complex number I. So this is exponential I by root.
So could we just do -1 to the 1/4?
Yes, you could do -1 to the, maybe if you want, I can rewrite it down. Rewrite it like this to avoid any confusion. Okay. So you can check that this funny combination of Parisi operators reproduces exactly what this cocycle gives you. And then using this, so the reason why would you want to do that is that then once you have it in this form, it is a bit easier to sort of check explicitly that these symmetry operators does commute with the Hamiltonian. It's immediate if you have it, if you kind of trust the definition and you work with the cocycle, but if you're given this Hamiltonian, then you probably want to rewrite it like this to check explicitly. Okay, well, I think that's everything I wanted to cover today. We will next week consider a generalization of this anionic chain picture involving what we call some module categories, and this will amount to then to considering dualities between anionic chains. So thank you. If you have any questions, further questions. Yeah.
So this, either in the abstract definition or in this one, when you choose these coefficients for the Hamiltonian operators, is there any restriction or could you just choose anything?
Yeah, that's a great question. If you want your Hamiltonian to be Hermitian, which you probably won't, then yes, you would put some constraints. I haven't worked out like an equation, a specific equation that you would need to satisfy to be Hermitian, because it depends a bit on like the labels and everything. But yes, this is one constraint. Otherwise, no. There was no constraint. Like as far as the symmetry is concerned, it's all taken care of by the other part of the Hamiltonian. These coefficients is just like different combinations of symmetric operators, but it's always going to be symmetric.
So here, if you put some random coefficients there.
No, that's the whole point. I could put A, B, C, and D in front of these guys. I would have a Hamiltonian that is physically probably meaningless, but it will have the desired symmetry. Yeah.
And the fact that you could, so to get the coefficients so that you reduce to transfer-free DC model, it was an art, or was it obvious it should have been just some?
No, that's a great question. This is not, indeed, this is not always easy. And often the difficulty, I mean, so next week we will see like some Heisenberg models which are a bit more involved. It's not necessarily obvious how to write it down in this language. But once you do, then you're golden in a sense, because then you don't have to worry about much anymore. It's just gonna work. Yeah.
What role does the choice of X play in this story?
Yeah. So let's say you take this Hilbert space, but then you for a finite group, right? Any finite group. If you choose X the way I chose it, which is you take the sum, you allow for all possible simple objects, then you're always going to get this tensor product structure. But if you choose, let's say the extreme other case, it would be to choose X to be the identity. This would force all the degrees of freedom at the bottom to be the same. This would be enforcing some symmetry broken phase essentially, because then your states are all tensor products of G's, right? So this has symmetry broken. More generally, you could say, okay, what if I pick a subgroup? And from that, you're going to get naturally the Hilbert space associated with the fixed point of a symmetry broken phase, but like not necessarily a whole group, like you're only breaking a subgroup. And this is not a coincidence, because there is a way of writing down for every possible symmetry and any sort of symmetry breaking pattern, if you want, you can write down a fixed point Hamiltonian, and it's going to amount to, in particular, to choosing a specific X. Yeah.
And also, so all the symmetry generators that you define, they act from the bottom so that they commute with the Hamiltonians that is acting from the top.
Yeah.
Could you also write down some other operators other than Hamiltonian that also act from the top? Maybe more non-local than your Hamiltonian.
Exactly, yeah. So these are going to be the like the charge operators, like the order parameters are going to be like this. You can think of the order parameter as being exactly as you said, some kind of a longer range type of operator, which will involve additional data. But yes, they will act from the top as well. Yeah, we can understand indeed these operators in that language as well. Yeah.
So, do you know if these are related to, say, the higher conserved charges of the integrable spin chain?
Higher, sorry,
so you can define the Heisenberg spin chain with the Hamiltonian, that's kind of local.
Yeah.
But then you can show that it has a bunch of other operators that also.
That come into the Hamiltonian, sure, yeah. Yeah, but I mean, these are usually charge, I mean, you have the charge operators and yeah, you can write them down as well. Like, yeah. Yeah. So we'll talk about these generalized charges next week. Yeah.
I have several questions about model examples of spherical categories which you consider. Apart from the categories which come from the representation theory, are there any other interesting? So the first question. The second question maybe is a response to the second question. Another type of solution of the highest associativity equation, like the Pentagon equation, are related with non-associative object or not co-associative object, like for example quasi-Hopf algebras, which are related with Drinfeld co-associators. Sure. Are there some models which are related with Drinfeld co-associators?
So, I mean, if you take representations of some some quasi-Hopf algebra, these are typically going to give you some fusion categories, just different, it's an equivalent language. So you could actually, there is a version that some people worked out, which is kind of an analog of this, but in the language of Hopf algebras. As far as the first question is concerned, so yes, I mentioned, I was going to write it down, but I skipped it. So another example of fusion category, for instance, would be this Ising modular tensor category, which are like 3 objects, and this corresponds to the 3 operators of the Ising CFT. And if you try to write down a model using this input data, you naturally get something that looks like the transverse field Ising model at the critical point, which is not a coincidence, since in the thermodynamics limit, you expect to find the Ising CFT. I mentioned this Fibonacci example as well, which is like a very small, I mean, it's nice because it has only 2 simple objects. This one is actually related to the tricritical Ising model. This was the first example as I mentioned. You can rewrite it in terms of temporally lib, and then it's related to various cases. You can work with some quantum groups as well, which is, again, more related to temporally lib. Like we will be mainly focusing on this kind of vec-G, rep-G type of examples because, well, the models that we write down in this, using this type of input, I can then also translate them explicitly in terms of spin operators, so I can establish a dictionary, right? Of course, this framework becomes really powerful when there is no nice way of writing down the Hamiltonian. So we did some examples, for instance, starting from like a higher up fusion category, which is more complex. The Hamiltonian, there is no way of writing down the Hamiltonians in any nice way, apart from this way, right? And then using this language, we are still able to do dualities and all, even though we are not able to really write down the Hamiltonian in an explicit way. So the framework really becomes... No, it is explicit. What I mean is that I cannot rewrite it in terms of like spin operators or something else. No, exactly. But so the examples I'm going to choose in these lectures are typically the framework will be a bit of an overkill, not always, but already a bit of an overkill because I want to be able to write them down in a nicer way. But the framework really becomes powerful when you have like models that are difficult to deal with, using traditional tools, let's say, right? Of course, yeah. Okay, if that's it, thank you for your attention.